it's been such a long time since I've posted anything. And it's just because, it's been super stressful, to be honest. I mean, we go through it too. I'm sure you guys go through it, right? School, work, extracurriculars, extra life stuff, just extra, extra everything. Just try your best. I don't think anybody could ever ask for more than just your best. And if they do, it seems kind of unreasonable. So here I am trying my best. This is lesson 6.2. We're going to go into the power rule. How quickly can you find the expression for the rate of change for the following? If we were to attempt to do limits or first principles, it would take forever. Okay, but because we have something called the power rule, it literally can take us 1 or 2 steps. So let me teach you how to do the power rule. Okay, if you have a function that equals to something with a power, what you can do is take the derivative, and all you do is you take that power and you bring it down, and it becomes a coefficient that is multiplying that x now. Then your new power is going to be just your exponent subtract 1. So it's going to be 1 less than whatever you had before. So let's do an example really quick. This is example number 1, I guess. F at x equals to x to the power of 8. If I want to find the derivative, I would take the 8, bring it down to the front. It becomes a coefficient that multiplies my x. Then you just do 8 minus 1. And so your new exponent is going to be 1 less than the exponent you had before. That's it. That literally would have taken like a million steps if you had done first principles. I know, teachers like to mess with you guys a little bit. Okay, we're the reason why you guys are stressed out, aren't we? The constant rule. So the constant rule is if your function is actually a constant, when you take the derivative, it's going to equal 0. That's because there is technically an x value beside it, but it's x to the power of 0. So x to the power of 0 is 1. Your c is multiplying 1, which makes it still a c. But if I apply the power rule, you'll start to see why you get a 0 on this side. So take the power, bring it to the front, and multiply it with whatever coefficient was already there. Okay, so that would be 0 times c, which is just 0. But we still have the x to the power of 0 with 1 less, right? And so even if I simplify that a little bit, this 0 is multiplying all this. Isn't that just 0, right? It's always going to be 0. And that's why, for our example, if the function is equal to 5, we know right away that it's a constant. So when I take the derivative, it's just going to be 0. Okay, so we're going to move on. The constant multiple rule means that if you have a constant and it's multiplying a function, if you want to take the derivative, that constant will still be there, but you're going to multiply the derivative of the function instead. So through our examples, we have 2 examples on the side. F prime at x, so I'm now taking the derivative. Our constant stays there, but I want to multiply the derivative of my function. So I'm going to take the 3, bring it down to the front. It's going to multiply my x, and then we're going to do 1 less than that exponent. We're just applying the power rule. If you can simplify it, just simplify it a little bit. X to the 2, and that's how I would leave it. Let's try that again. So f prime at x, leave the constant alone, okay? And then you're going to multiply it with the derivative of your function. Okay, so we can apply the power rule. The 15 is going to come to the front. 15. It's going to multiply your variable to the power of 1 less than what it was before. So you're going to get 15 over 2x to the power of 14. Now, if you get this right away and you don't want to write all the steps, what you can do instead is say 3 is going to come down to the front. It's going to multiply to give you 15, multiplying the x, but you're going to subtract 1 from the exponent. So notice that it's just the exact same thing, but you just skip this step. So it's really up to you. Once you get used to it, I don't even do that step that I just crossed out. I just jump to the answer right away. Okay, so I'm going to show you 2 last rules. These are called the sum and difference rules. Basically, if you have like a ginormous function, we'll just call it h at x, but it's made up of the sum of two smaller functions like f at x and g at x. What you can do is take the derivative of each one. So you have the derivative of f at x plus the derivative of g at x. In other words, you can either take the entire thing, put it together, and then do the derivative, or you can take the derivative of both of them separately and then add them together. Okay, so here's an example. H at x is equal to a purple function plus an orange function. So if I want to take the derivative, I can take the derivative of each of them separately. Okay, so I'm going to take this guy, bring it down, because that's the power rule. We're going to apply the power rule. It's going to multiply the 6, and I'm going to get 30. X to the power of 1 less than the 5, so 4. So I just applied the power rule, and that's the derivative for the purple. Plus, the derivative for a constant is just 0. If I clean it up, I don't want that, right? So just 30x to the power of 4 is our final answer. Same thing goes with the bottom. Saying the exact same thing, I could either subtract them both, not both, that's not a word. Okay, I can either subtract both the functions first, then take the derivative, or I can take the derivative of each one separately and then subtract them. Okay, so let's just say h at x is the purple minus the orange. So you have two different functions combined together to make this h at x. If I want to do h prime at x, I would do the power rule, and I would multiply the constant by my exponent. That's just going to give me 8. X to the power of 1 less than the 16, that's 15. Okay, so that's done. The purple derivative is right there. Now we're going to take the derivative of the orange. Okay, so this one has an exponent 1. Let's do the power rule. 20 times 1 is 20. X to the power of 1 less than the exponent would be 0. So I don't really want to leave it with an x to the power of 0 because we know that that's equal to 1. I would go one step farther and I would say 20 times the 1 is just 20. So I'm going to leave it just like that. All right, now those are all the rules. If you want to see a shortcut now for those first two questions, I think we can do them pretty quick. Okay, so if we wanted to do h prime at t, we can do the derivative of this guy first, pull the 2 down. It's going to multiply the 3, so I'm going to get 6. X to the power of 1 less than the 2, so just 1. This guy's going to be next, and you know that that exponent with the x is a 1. So we're going to bring that down, multiply it with the 8. So you're still going to get 8, but now you're going to get x to the power of 1 less than the 1, which is 0. And the derivative of any constant you guys know is 0. Okay, so we're going to clean that up a little bit. I don't want you to write the 1. I don't want like a 0. This is just ridiculous. Okay, so your answer should be 6x plus 8 times 1, which is just 8. Okay, so like I said, we don't really need limits. We can do this within like a step. And then even though this next one looks ridiculously crazy, we can do it. P prime A is equal to, apply the power rule, so the 4 times this entire fraction. So 4 times 5 over 3 is 20 over 3. A to the power of 1 less than the 4. Plus, I don't know if I can see that. Is that a quarter? I think it's a quarter. We're just going to say it's a quarter. 1/4 times 12, which is 3. A to the power of 1/4 minus 1, what is that? Equals to negative 3 over 4. 3 over 4. Okay, plus, and then this one has a 1 exponent, so let's bring that 1 to the front, plus 1a to the power of 0. And then this is just 0. Okay, and now we're going to clean that up because don't want this, don't want this. And any negative exponents you should really make positive again by hiding it in the denominator. So I'll show you how to do that. 3a to the 3, that guy was fine. plus, now I don't want that negative exponent, so this 3 can stay in the numerator, but this entire thing has to be shoved into the denominator because it had a negative exponent. So when you put it back into the denominator, it's no longer a negative, right? Because it's a reciprocal. Okay, I'm hoping that you guys have learned that already. Plus, a to the power of 0 is 1, so that's just a 1, and that 0 I'm not even going to bother with. All right. This is the proof of the power rule. I am not going to go through this with you because I'm just going to slowly scroll and you guys can take a look. If you guys are in my classes that I'm teaching at the moment, feel free to ask me what all of this means. But essentially, at the very end, you get the power rule by doing all of first principles. Okay, let's do some really quick examples. We've done like 5 million. Why don't we do another 5 million? So, jumping into the derivative, I'm going to go f prime at x equals 2, and that's a power. So, a power function. So I'm going to take the 21, bring it down to the front, and it becomes a coefficient that multiplies the x. Then you're going to go 1 less than the exponent, so 21x to the power of 20. Do you have to write that upper step? No. Okay, do I want to show you in a video just in case? Sure. Since this next one started with a y, I think I'm going to do the same. Y prime is equal to, bring that 8 to the front, it's going to multiply your coefficient, then you're going to have the x, and then 8 minus 1 is 7. Okay, now that one looks weird. Okay, example number 3. This guy is just saying the derivative. So they want you to find the derivative of a to the power of 10. So we're just going to say that that equals to bringing the 10 down to the front. Okay, so you're going to get a to the, no. Let's get rid of that. 10 times a to the power of 9. So 1 less than that 10. Here's where it gets a little bit more crazy. I am going to need more space for the last one, so I'm just going to extend the page a little bit. And we're going to go back. There we go. Okay, example number 4. Example number 4, you know what? It gets really complicated when it's in the denominator like that. Here is a trick. If you rewrite this function so that it's not in a fraction, it makes it so much easier to do the derivative. Let me show you. So I'm not doing the derivative yet. This is still f at x. But I don't want this in the denominator because it makes it really complicated. I'm actually going to knock it back up to the numerator, but then I have to show that this is actually a negative exponent. So if you went the other way, you know that x to the power of negative 5 would have been 1 over x to the power of positive 5. So I just decided to rewrite it, but not in a fraction form. If I wanted to take the derivative now, it's so much easier because I can just take this, bring it down, okay, and I get negative 5 x to the power of negative 5 minus 1, because it's 1 less than what the original power was. Negative 5x to the power of negative 6, and this is pretty much done, but you'll get marks taken off if you leave that negative exponent. So make sure, again, just hide it back into the denominator at the very end as a positive exponent. The next one, example number 5, same sort of thing. Like that root really bugs me because it doesn't look like a power function. And so I'm just going to rewrite it. I'm not going to take the derivative yet, but I'm going to rewrite it with an exponent that means square root. So the square root is anything to the power of 1/2. I haven't done anything, I just rewrote it in the exponential form instead. So to take the derivative, s prime, I'm going to take 1/2, bring it down to the front. It becomes a coefficient in front of the t, and then you take the 1/2 and you subtract 1. So that's 1/2 t to the power of negative 1/2. And again, I don't want that negative exponent, so I'm just going to bury it in the denominator. So that 2 is already in the denominator from the 1/2, but now the t is going to join it with a positive exponent of 1/2. Now the last one looks fine, like it's not a fraction, it's not a root, so I think I can just apply the power rule. Y prime is negative 60, u to the power of negative 7, because it was a negative 6, minus 1. And again, I don't want that negative exponent, so I'm just going to write this to make it look prettier in the denominator with a positive exponent. So now that you've tackled those, I think you can probably tackle this crazy one. I know it looks really crazy, but it really isn't. All you have to do is it looks like a giant polynomial. Just get rid of all of the roots and the fractions. Write them instead in different kinds of exponents. So don't do the derivative yet. G at x. This one's fine, so just leave it. This one, though, has a root. So I'm going to convert it into a fraction exponent. This guy is fine. I don't want to touch it. 3 x to the power of 3 over 2. This one is also fine. It doesn't matter if it has negatives yet. I just want to deal with them at the end. So 2 to the power of 2 times x to the power of negative 4. This is all tricky. They decide to throw a constant in there, 99. Okay, and this last guy right here, that's going to be a little bit tricky. That's 8 over 3, positive, with an x to the power of negative 3, because I want to bump that x to the power of 3 back into a numerator. So I have to write it with a negative exponent. Okay, now that everything is in a nice long row, you can do the power rule for all of those terms. G prime at x is equal to, do the derivative of this one first. Bring the 4, 28x to the power of 1 less. Plus, do the derivative of this one next. 1/2, bring it down to the front, x to the power of 1/2 minus 1. I'll deal with that later. Okay, now this guy. Multiply the front, negative 9 over 2, x to the power of, and then your exponent, minus 1. Now this guy. Minus 2, nope, no. Too fast. Don't go too fast. Okay, so this guy, multiply that one. Positive 8, my mistake. X to the power of negative 4 minus 1. Derivative of this one is just 0, so I'm not even going to write that. And then this last one, multiply the whole constant in front, negative 8, x to the power of negative 3 minus 1. Okay, let's clean this up, because all of those exponents we probably should solve for. 28x cubed plus 1/2 x to the negative 1/2 minus 9 over 2 x to the power of, what is that, 1/2 positive, plus 8 x to the power of negative 5 minus 8 x to the power of negative 4. Okay, so now everything's looking nice and clean. Just make sure that, you don't have to change everything back into roots. Anything with the fraction exponents, don't change them back to roots. Just show like these steps, because then it makes it very easy for your teacher to see what you've done in each step. The last part I would deal with is just no negative exponents. So this one's fine. This one, I'm going to embed that x to the power of 1/2 positive into the denominator. Minus 9 over 2. Whoops, made that a little bit long. X to the power of 1 over 2. Plus 8 over x to the power of 5. Minus 8x to the power of 4. All right. Now, if you were to have done that with like first principles, you would have to live at school. Like, I don't know how you would do that within like your lifetime. That would take forever. So, derivatives so much easier. Okay, let's go into a word problem. So find the equation of a tangent to, and then they gave you an original function, at x equals to 1. So include a sketch. Check with the Nspire. You guys can do that on your own if you want. Let's go through the steps. Number 1, you want to find your slope. So I'm going to use a certain color for that. Why don't we say y prime? Okay. All right. Now in order to do y prime, you're going to have to do the derivative. So y prime is equal to, again, power rule, 6x to the power of 1 minus, this has a 1 here, so bringing that down, 4, x to the power of 0, right? And then derivative of this one is 0. So equals to 6x minus 4, and the rest of it just disappears. So this is your equation for all slopes. Now they didn't want all slopes, they actually want a slope at x equals to 1. So we know what this is. Why don't we just put that in? So y prime, but with a 1, is going to be 6 times your 1 minus 4. And so your slope is 2 at x equals to 1. All right, therefore, slope is 2. I probably need a point as well. So if I do the point, let's see, number 2. Let's find a point. Find. What is the point when your x is 1? I don't know what my y is, so maybe we should find that. All right, so we're going to use our original formula for x plus 2, but wherever I see an x, I'm actually going to get rid of that and put a 1 instead. Okay, so you're going to get some sort of a point at 1 and 1. Now with all this information, you can then find the equation of the tangent. Okay, so number 3, equation of tangent. Let's move that down a bit, because really all I need is a point and the slope. Y equals mx plus b, because your tangent is a straight line, right? You're going to take both of your point numbers, so the 1 and 1 equals, and then you have your slope is 2, right? Plus b, 1 equals 2 plus b. Bring that over, you're going to get a b of negative 1. Therefore, the equation of your tangent is going to be y equals to 2x minus 1. Now, if I'm going to draw something like this, what it would look like is, first of all, your original formula is some sort of a parabola. I think it might look something like this. Okay, this is your y equals 3x squared minus 4x plus 2. Now, what you want is at 1, x equal, when your x is 1, you get a point right here at 1 and 1. Right? Now, what we were trying to find is that tangent, and that tangent skims p just ever so slightly. And that slope is 2. So the equation of this orange line is this guy right here. That's what you found. Okay, so I gave you the next example. Given that you have a certain function, so h at x, determine the x values that have horizontal tangents. So I'm just going to show you what this kind of looks like. I think, let's see, it looks something like, I don't know, I'm just roughing it. So something like this. Okay, now you have certain tangents, and the tangents are, you have increasing tangents like this all along, right? But there's certain places on the graph where you have 0 slope. Like the slopes of those tangents seem to be positive right now, they're going upwards, but right at the peaks are where you have 0 slope, as in like no steepness. So what they're asking for are, what are the x values at those specific points? Okay, so what we have to do is we have to find the derivative, that's the slope formula. So this formula right here is the formula for all slopes everywhere along that polynomial function. And then what we have to do is if you want horizontal tangents, you're basically looking for a slope of 0. And that's why we put 0 right here into your slope. So we can start to solve by factoring. Okay, so notice that I have this guy right here, and that gives me an x value of 0. That's probably this one right here. Okay, so x equals to 0 is right here. Then solving this other one using the quadratic formula, I actually get negative 2.08 and 0.48. So this one right here is probably the negative 2.08, and this guy right here is probably the 0.48. Okay, now they didn't ask for coordinates, but if you did want coordinates, you could always take these guys, all your x values, and plug them back into the original function wherever you see an x. And so you get these 3 points. Okay, so let's do one last question. I know I haven't actually made a video in a long time, so I have to talk and talk and talk, right? Find the equations of the tangents to k at x such that they pass through the exterior point 3, 2. Okay, what this is basically saying is you have an original function, and that is some sort of a quadratic, and it might look something like this. Okay, so this is k at x. Then what they want you to do is they want your tangent to pass through this. So 3 and 2, maybe, I don't know, 3 and 2, somewhere like right here. This is going to be your point P, that's a P. So you could have two tangent lines, one of them that just skims this way and touches somewhere up here, or it could actually skim this way and just lightly brush right there. So there are technically 2 points along your parabola that could go through P, but then also is a tangent to your blue parabola. And so what we have to do is we have to find the equation of both of those tangents. You know what? I think I want to call this Q, but then also I guess this point could also be Q. So let's go through everything. I have Q as whatever the coordinate is going to be with your x value, and whatever your x is going to be subbed into k at x. So you're going to find some sort of point for Q. Your second step would be to create an alternative expression for the slope using P and Q. So we already have like K prime as being the slope, but I want to find another way to find the slope. So you could find the slope by doing y2 minus y1 x2, sorry, that's not even, I don't even know what I'm writing now. What am I writing, guys? I have no idea. Okay, do it this way. y2 minus y1 x2 minus x1. So we could use a regular slope formula and just find an expression. Then we can actually make them equivalent. So this expression is the same as k prime. Okay, so k prime, I'm sorry, I should have done that before. Let's go back up. K prime is just taking the 2, bringing it down. We'll do the derivative using the power rule. Okay, so what is that? 2x to the power of 1. This was a 1 up here, so let's bring that down. Minus 1x to the power of 0. And then the derivative of the 4 is just going to be 0. Equals 2x minus 1. Oh, that's where they got it from. There it is, right there. Okay, so making those two equations equivalent means that I could start to solve for x. And if I have x, I can find out what my q is. All right, here's a quadratic formula. So I found my x, and I actually have 2 answers for x. And so my slope, plugging those back into the slope formulas, give me two different slopes, because you remember we had two tangents before. So putting it back into the slope formula, subbing this into my x of my slope formula, subbing this one into my x for my slope formula, gives us two different slopes. And if you'll remember what this looks like, because it was some sort of a parabola like this, there was one with a negative slope, that's probably this guy. And then there was one that had like a positive slope, that's probably this guy. Now that we have both slopes, we can use the points, because the P was actually on each of the lines, right? We can use a point and we can sub in everything into y equals mx plus b and get our two equations. Okay, so you can either leave them with this is your slope and your y-intercept, slope and y-intercept. So you get two answers because there were two tangents. If you want to put them in decimals, you can put them in decimals. Okay, that was a major lesson with all sorts of examples, but I think they taught a really great tool, which is the power rule. Okay, so tune in next time. We will go into product rule.